In this video, I'll evaluate the fatigue life in a steel bicycle frame and optimize the frame design using ANSYS AIM. I'll begin by selecting the structural template, enabling geometry modeling capabilities, and selecting the option to compute fatigue results. The CAD model includes the full bicycle assembly. Using AIM's built-in geometry modeler, I'll unselect the parts which are not required, leaving only the bicycle frame, seat post pin, and front fork. I'll also create a parameter to drive the design changes. Using the pull tool, I'll create a parameter that will automatically adjust the thicknesses of the frame tubes. With the geometry preparation complete, I'll proceed to the next step of the simulation workflow. Using AIM's automatic meshing, I'll quickly generate a high-quality mesh for the bicycle frame. For this mesh, I use the curvature size function to automatically resolve curved surfaces. Next, I'll define a support boundary condition where the frame is supported by the rear axle. I'll also define a support where the front fork rests on the front axle. The weight of the rider is represented by a force applied to the top of the seat post. Per an industry standard fatigue test, I'll apply a downward force of 1400 newtons. AIM's automatic contact interface generator makes it easy to account for the interactions between the parts of the assembly. AIM automatically detects contact between the frame and the adjacent parts, as indicated by the red color. Next, I'll solve the model and review the fatigue results. First, I'll review the displacement of the frame. The deformation is automatically exaggerated for display. The results can also be animated to see how the bicycle frame deforms under the applied load. Next, I'll review the equivalent stress in the frame. The maximum stress occurs behind the seat post tube. I'll also review the fatigue life. Industry standards dictate that the minimum fatigue life should be at least 100,000 cycles. The results show that my design is well above that threshold. Therefore, I'll modify the design to reduce the weight and material costs while maintaining the minimum fatigue life. Next, I'll return to the geometry task to modify the model. I'll simply change the tube thickness parameter. I'll try a tube thickness of 1 mm. All of the frame tubes are automatically modified, and I'll quickly update the simulation results for the new geometry. Reviewing the fatigue life, the minimum is far below the design threshold of 100,000 cycles, so reducing the tube thickness to 1 mm wouldn't be safe. I'll try a more modest reduction in the tube thickness and use 1.6 mm. Again, the geometry is easily modified, and the results are automatically updated with just a few mouse clicks. The minimum fatigue life is now slightly above the design threshold. I now have an improved design which satisfies the fatigue life with a lighter weight and lower material cost. With ANSYS AIM, evaluating and optimizing product performance is quick and easy. Thank you for watching this demonstration of ANSYS AIM.